streaming. All right. All right, so the first thing is, to initialize the stack pointer. Technically speaking, where you put this really doesn't matter. But we are going to, implement the subroutine in the same order. So I'm going to put main later on and not worry about that at this point. So here's, function f, or Fibonacci. It has one single parameter, which is n, that is on the stack. And then we have the usual return address on the stack. And at the entry point of the subroutine, register D, which is our stack pointer, points to the return address. Is that part okay? Yes? It should be kind of boring at this point, okay, because we have done this many, many times. All right, so I'm going to implement the C code the way it is, so I'm not going to convert it into conditional statements to do it. So the first thing we need to do, when it comes to what, the sequencing of how to do things, is we have to compare n to 2. So with this one, we first do a CPR CD. So this way we can access n without modifying d. Okay. So I make a copy of C, and it really is helpful. If you guys did not do it, that's fine. But if you, I think if you have a chance to go back to your own code to document it, that might be helpful. So at this point, C is the same as D, which is the address of the return address on the stack. If I increment C, it becomes the address of n, which is not n. This is just the address of the parameter, but it is not the parameter itself. So I need a dereference. Both LD and ST can dereference, but their purpose is different. LD is for reading dereferenced, and then a store is for writing dereferenced. Okay? So in this case, LD is more appropriate. Let's see. I don't really need to get back to the address of n anymore. So I'm going to store that back into C. So the C is now just n. And now I can do some comparison. So LDI A with 2, and then we just do a comparison. So we're comparing A with 2. And then we have to do a conditional branch to somewhere. So this is where we can kind of craft our conditional branch according to the C code. The C code says when n is less than 2, we go to one case, and when n is not less than 2, we go to another case. We only have JCI for unsigned comparison, to indicate less than, and JLI for signed comparison. Okay, so it is more helpful for us to use a JCI in this case. So let's do the compare first. But we know that we want to use a JCI to some place. So that means the ordering of the compare is really comparing n, which is in register C, to the value of 2, which is now currently in register A. So I'm going to perform the comparison like that. If it is less than, if A is in fact less than 2, then I'm going to go to the then branch. Okay, so I'm just putting a label here called then value. If not, I am going to the else value. Okay. Now I do not have to do it this way. Okay, I can certainly just have the else value code here directly. That works too. But this way, the labeling, will help me identify which section of code is doing what. So there are different ways to do it. I just think that this way may be more clear, when it comes to understanding the code. But there are certainly different ways to do it. All right, so then value is going to be defined here. That is easy. It's just n itself. So that means, I could have done it even, in a more streamlined way. Because, do you guys want to continue with this one, or do you want me to do it in a slightly more streamlined way?
Yeah, change A to B, right?
Yeah. Okay. So do you want to continue with this one? Okay.
I wanted you to change the B with the...
Change it to so it's more optimized? Okay. So I have to change the code accordingly, or the comments accordingly. So this way, the nice thing about this, that's A, that is B. Okay. So if I change it like this, then by the time we get to then value, there's nothing to do. because the value of n is already in register A, and register A is what we use to return a value to the caller. So that means I'm done here, okay? So you can just do a JMPI all the way to the end of the conditional statement. I would just call it end if. Now obviously this can also be optimized later on, so I'll optimize this later. But for now, I'm just gonna continue with the else code, which is the problematic one, right? That's the long one that is a little bit more time consuming. All right, so we are now focusing on just this part, okay? So the question now is, how do we do it? Well, we can only do one thing at a time. So that means it doesn't really matter. You can handle, the Fibonacci of n minus 2 first if you want to. You can also handle, n minus 1 first if you want to. It doesn't really matter which way you go first, okay?
Is that because they all are technically one argument or whatever? Is that like one comes before the other?
That is correct. It's also because addition is commutative. And the compiler actually has the freedom to change the ordering of the values that you're adding. So the compiler can evaluate the second part of the addition and then the first part of the addition and then add it together. There's no guarantee that it has to read from left to right when it comes to addition and so on and so forth. The only time it is guaranteed from left to right is when you have logical operators because of short-circuited evaluation. But in addition, there's really no short-circuited evaluation, so the compiler can change the order, and your code has to be written in a way that it should not matter which way it goes. All right, so, but I'm going to read it from left to right, so we will deal with n minus 1 first. So here, we compute n minus 1. N is already in register A, so we just need a decrement A. So this way, A is n minus 1 at this point. And then we can push it on the stack, which is just decrementing D and storing A to wherever D points to. So this way we are basically pushing n minus 1, the value of n minus 1 on the stack. I'm not changing n. I'm just changing a register that contains the value of n minus 1 in this case. Push it on the stack. Then we need a LDIA, we'll call it F, return from first call, okay? And then we'll define the label here, F return from the first call to F itself. So this is a label definition. Push it on the stack, like so. So now we have the argument on the stack, we have the return address on the stack, it's ready to go to call the subroutine. Calling a subroutine from itself is no different from calling any subroutine. That really is one of the main points that I want to make in this particular homework assignment. It doesn't make a difference. We do exactly the same thing. If there are arguments, push the arguments. Push the return address, and then do an unconditional branch to the very beginning of the subroutine. Same thing that you do with calling any other subroutine. When it comes back, technically, we have to clean up the stack, okay? Now, in this case, cleaning up the stack, we kind of have to look at this a little bit kind of carefully because, or if you want to optimize, we also want to look at this a little bit more carefully. Because there are two things that are involved here. First thing is, when it comes back to this label, register A has the return value of that invocation, okay? So register A is important, okay? The second thing is, the stack is now pointing to, the stack pointer is pointing to n minus 1 right now, and I need n minus 2 for the next call, okay? So all of those things can be potentially useful, so I just have to be careful of, okay, do I want to destroy the one to save the other one, or what do I want to do? Is that okay? So what I'll do is I'm going to retrieve what is on the stack right now. Okay, typically when we deallocate arguments, this is all we do, right? Because by increasing the stack pointer by 1, I'm quote unquote deallocating that 1 byte that is currently being used by the argument, which in most cases it's no longer of any use. But in this case, hey, guess what? It has got something that is really close to what I want to use as my argument for the second call to Fibonacci. So I may want to do something like this before incrementing D. I still have to increment D, but I'm going to do this first. I am going to retrieve that into a register B or C, okay, at this point. Is that okay? Because A used to be n minus 1. It's definitely not n minus 1 now, because it is now the return value of the invocation with n minus 1 as an argument. So the content of A is guaranteed destroyed at this point. So in order to get back to n, I can either go through this whole exercise again, do a CPR, CD, blah, blah, blah. Okay, I could do that. But since, that value is already sitting on the stack, I just have to subtract 1 from that. I might as well just use it on the stack. Okay? Okay, so let me just make it very clear what is in register B at this point. After this, B is n minus 1, which is very handy because I need n minus 2 as the next argument. I increment D, okay? But then I think about this and go like, oh, I need to save that register A on the stack too, because register A has the return value of f of n minus 1. I have to add that to the return value of f of n minus 2. But the call to f of n minus 2 can potentially destroy all of my registers. So I need to save the return value of f of n minus 1 somewhere, so that when I get back from the call to f of n minus 2, I can then retrieve it and then do something with it. What is the best place to save something? The stack. All right. So here, I'm going to save it on the stack, which means I'm decrementing the stack pointer again. And then we store to whatever the stack pointer is pointing to, register A. So I'm saving, okay, I'll make it more clear. We are pushing the return value of f of n minus 1 on the stack. But then you look at this code here and go like, oh, that is not doing anything that's useful. We're incrementing, and then we immediately decrement. It's perfectly safe to get rid of these two instructions at the same time. You don't think so? Why not? Interrupts is not going to have any effect here. Because if you get rid of both of these instructions, D is never changed, right? So interrupt can happen all it wants, because all it can do is to modify everything that is below it. Is that making any sense? Okay, so the question is, can I remove the instructions on line 26 and line 27? And the answer is yes, I can, even when interrupts can be happening. Because if interrupts is happening, let's say immediately after the load instruction, it's okay. The stack pointer has not moved, so everything that I care about is still on the stack. Is that okay? So the only time you have to do incrementing and decrementing of the stack pointer is when you really want to get rid of something on the stack. Okay, it's of no value to you anymore. And the only time you need to decrement D is when you are allocating space for something else that you will store later. So in this case, I can get rid of the increment and the decrement without any worries. So interrupt is not actually going to be an issue here. So I'm going to do this. I will just kind of comment it out so that we can see that they could be here, but it's not going to be useful for anything. Okay? All right. So now we have saved the value of f of n minus 1, and we have retrieved n minus 1 itself into register B. What do we need to do? In other words, we are done with f of n minus 1. What do we need to do next? Call Fibonacci again with n minus 2 as the argument, right? Okay, so we decrement register B. So the B is now n minus 2. Push it on the stack. Push the return address on the stack, LDI F return from second. F return from second is here. So put it decrement D and then store to where D points to. So now I have pushed the return address, and now we are ready to continue execution to the subroutine that we are calling. Well, the fact that we are in F and we are calling F doesn't matter, doesn't change how we do it. Do we have any questions about this code at this point?
So far, you haven't written the what happens after you're going to return.
Correct. I have not written the code after the return from the call to f of n minus 2. That is correct. But are there any questions?
The return point, right? When you call F, where does F return to right now? We don't have anything, right?
It returns to f return from second,
Well, I mean, like
the label.
what does F do?
There's no code there.
Yeah. Okay.
Yeah. Okay. So when it comes back, this time I can just increment d to get rid of the argument that is on the stack, because the value n minus 2 is absolutely of no value to me anymore. Okay, because I'm done with all the calls to recursive calls, so I really don't need n back anymore. The return value of, so I'm going to just write here, register A contains the return value of f of n minus 2. Where do I find the return value of f of n minus 1? I put it somewhere. I stash it on the stack. Very good. So now I need to do a LD first. So I'll put it into register B because I don't want to destroy register A. Register A is really useful to me. So I'll put it back into D, okay? So that after this, B is the return value of f of n minus 1. Increment the stack pointer, okay? Because that is just me saving the return value on the stack. Now that it is retrieved, I don't need that on the stack anymore. So I have to remember to increment the stack pointer. And then we just need to do an add instruction. We are adding D to A, okay, so that the sum is automatically stored in the register that is going to serve as my return value register. And, huh?
What are we adding? A and what?
Huh?
Which register are we adding? A and A plus.
We are adding D to A. Oops. Oh, that's right. We're adding B to A. Thank you. We're adding B to A, not D to A, because B has the return value of f of n minus 1. Thank you. So this completes the else case. And we can just fall through to end if. The end if here is just the usual return, which is LDB. I cannot use A anymore because A contains the return value. So we have a LDB D, increment D, because now we don't need the return address on the stack anymore. We just put it into a register, and then JMPB will return back to the caller. What if the caller is in F? I don't care. It's the same steps. Absolutely the same steps. So are we okay so far with this? Now, you can see that there are some totally unnecessary branches that we can just kind of avoid, particularly up here. Look at, okay, I'm just going to point out this chunk of code here. Okay. If you look at this chunk of code, is there any way for me to optimize this code? Okay, especially when you look at the JCI. JCI goes to then value, which then executes the unconditional branch to end if. Does that sound a little bit redundant to you? I branch to here, and then that branches in return directly, unconditionally, to some other label. So when you see a chain of branching like this that involves unconditional branches, you can just go ahead and go like, okay. We can just shorten it because we don't need this anymore. We can just get rid of this, and the code is now a little bit cleaner, but not as clean as it can be, because we still have this crazy thing here that if we do not do the JCI to end if, we do an unconditional branch to else value. But where's else value? Right next door. I'm hopping on a bus. Okay, it's not really quite the same thing, but it's totally redundant. Okay, something like that. Yeah. So once again, this can be optimized out. Okay, there's no need for this. So now my code is a lot cleaner, but it's also a little bit more difficult to read because when you look at the code itself, it doesn't quite indicate what it means when we're here. So technically, I usually just go like, this is where we get to when n is less than 2 is false. So I like to remind myself what is this branch representing. With the labels, it is clear, but without the labels, it is a little bit difficult to understand. Okay, what does it mean when we are here? So I like to leave behind some comments to remind myself. So are there any questions about the code? This is the Fibonacci part, okay? So now we have to actually implement the main part because otherwise there's no way to actually test this program. So main is here. And the first thing we do is decrement D because we need to allocate for the local variable x. And then we need to call f with something. So we want to figure out, what is the largest value or the largest parameter that we can pass to f that will still be within the range of values that we can represent using an 8-bit unsigned integer, okay? Because that would be a pretty good test, right? So, okay, let's figure it out. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, and I think at this point I can move it over a little bit. 9, 10, 11, 12, 13, 14, 15. Okay, I think that should be enough. F of 0 is 0, f of 1 is 1, f of 2 is the previous 2 items added, so that's just 1. The previous 2 item added, 2. The previous 2 item added, 3. And this is 5. This is 8. 13. 21. 34 is correct. What's this one? 55. It's not tricky. It's 144. Okay, I need more spacing now. What about this one? 2. Okay. Okay, so 14 plus 9 is 23, and then 4 plus 9 is 233, and that's the last one we can do. Because beyond this, it's going to be more than 233. It's going to be, it's going to be more than 255, which we cannot represent using an 8-bit number anymore. So the Fibonacci number of 13 is the most we can do given that we're only using 8 bits to represent values. Okay? Is that all right? Yep.
And does that guarantee we can do it with enough space for our instructions?
Well, that's a very good question. So now the question is, how deep is it going to get, right? So the Fibonacci of 13 depends on the Fibonacci number of 12, and so on. So we're going to have, in order to figure out the Fibonacci number of 13, we will have 14 levels of calls to Fibonacci. Okay? So 14 levels times the number of bytes we need for each level is kind of the estimate. So for each level, we have 1 byte for the argument itself, 1 byte for the return address. That's mandatory. And then we have 1 more byte to store the return value of the first recursive call. So we have 3 bytes per invocation that we're going to use on the stack. So 3 times 14 is 42. So we're going to use up about 42 bytes on the stack, which is not too bad because I don't think this program is that big. It looks kind of big, but even if you assume some of these instructions are 2 bytes and some are 1 byte and labels do not take up any space, the program up to this point, excluding main, is only about 42 lines. So I think we got enough space to do it. All right, so moving on. So we just have to figure out, we want to do f of 13, right? So we push 13 on the stack. So LDIA with 13, decrement D, store to where D points to A. That pushes 13 on the stack. Okay, I'm just going to write it here. Push 13 on the stack. And then we do a LDIA with main return from F. Main return from F. That's a label definition. Decrement D store to where D points to. This is pushing the return address on the stack. Now we can just continue execution in F, JMP IF. When it comes back, we have to increment D to get rid of the argument on the stack because I don't really need it back anymore. And then we can do stda because the stack pointer should be pointing to local variable x at this point, which is going to be location 255. And this should complete the whole thing. So now it is just a return 0 thing, which is LDIA with 0. And we deallocate the local variable x, so we increment D one more time, and then we do a halt here instead of a usual return because main has no place to return to, and that should complete the entire thing. With the stack pointer completely balanced, okay? All right, so let's give it a try, see what happens. So Control A, Control C, go to my, oh, this is for another class. This is a trace of the A star algorithm. Yep. In CISP 440. Oh, interestingly, I was talking to a math professor today, and apparently there is a big shakeup in terms of what classes they will be offering. Some of the lower division classes, like the 100 series classes, will not be offered anymore. They will only they will only offer transfer level classes and not the remedial level classes anymore. So some of the math professors will not be able to make load because they're cutting back courses. Um, it has to do with the AB or assembly bill. I think it's a 705. Yeah, so yeah, it is AB 705. Yeah, you can read about AB 705. I think the intention is not the problem. So if you read the intention, it was written to clarify existing regulation to ensure students are not placed into remedial courses that may delay or deter their education progress unless there's evidence to suggest otherwise. Okay, so now the question is, how do you collect that evidence otherwise, right? Okay, so you got a few ways to do it. You can do an assessment test, okay, and ask every single incoming student to take the assessment test and go like, okay, let's see where you're at, and then we'll get you to the right class to start with, okay? But apparently that is not what they want to do. So what they want to do is to push everybody into a transfer level class first. If they fail, then you put them back into a remedial class. Then it becomes a waste of time, and it is even more demoralizing than telling a person to go like, huh? Well, if they retake that class, the new grade will overwrite the old grade. Yep. Well, the argument for AB 705 is evidence suggests that community colleges are placing too many students into remedial classes or remediation that significantly more students would complete transfer requirements in math and English if enrolled directly in transfer level classes. Now, this is just me being a conspiracy theorist and all, okay? But I think this has to do with making the numbers look good. Okay, they're trying to push more students through transfer level classes without remedial classes, so this way the number looks good.
But what happens when the GPA or like the regular fail rate just raises so high? I mean, you're going to shut all these kids that aren't ready for it at the same
Then we're going to hit them, the community colleges, with this thing. It's called performance based funding formula. So we are gonna. So then we'll punish the colleges, who report back and go like, "Oh man, many of our students who got pushed into 300 level classes are failing out. Guess what? You're not gonna get your funding, or at least the portion that depends on performance." Whack. So what do you think? What? Okay, so let's say we have a college district that is fiscally oriented. Okay, in other words, we don't want to lose funding at all. What do you think that college district is going to do when they have quote unquote performance based funding that says, huh? No, they just exactly, they can lower the standard, make the number look good to themselves, to the district, and everybody is happy. See, we got more people directly getting into transfer level classes, and they are successful as well. So who's down the chain who's gonna go like, oh no, not this? The the UCs and the CSUs, because they're gonna get these students into their classes as juniors, and they may not actually be at the level that they think they are. So this is just put, as they say, kicking the bucket down the slope, right? It's like, okay, not my bucket anymore. Now, as I said, it could be just completely my conspiracy theorist nature, thinking about these things in the wrong way. Yep. Oh no, I'm not. I was.
He doesn't want to get shot. He can't run. He can't run. Don't shoot him.
I'll push for binary numbers in elementary school.
I'm down. I'm down.
Hmm?
Whoa.
Yeah, I just came back from a union meeting, downtown, and they were talking about lots of interesting things,
Okay.
like the online college thing. Have you guys heard about the California online college?
What?
Yeah, well, okay,
California has an online college, huh?
not yet,
Oh.
but it is proposed. So Governor Brown and the state chancellor of community colleges are deciding that, hey, we're going to make a fully online community college. We are not talking about funding for ARC or Sac City to strengthen the online offering. We're talking about a completely online college.
Whole new staff, whole new building, whole new headquarters, whole new everything.
Yep, and I think the funding model, or the model for people to pay into it, is like they pay X amount of money, and then they can take as many classes and whatever classes they want to take within a certain time period. It's
How does that affect their ability to transfer, though? That sounds like it destroys their
it is
career.
not designed for transfer purposes. This is mostly for people who are already in the workforce and they're trying to strengthen their
So that's how they're
understanding of
getting
stuff.
rid of all the remediation. They're going to get rid of remediation and put it all online.
I don't know.
That's what it sounds like. They're going to push people who are in the workforce, people don't want to transfer into a finish up and do a higher degree, just want to take a class online.
No,
So
the
that puts the remediation
well,
online then.
okay, I know that AB 705 was originally targeting mostly high school students. They're targeting fresh incoming students from high school, and they want to say, okay, if you have taken a particular class in high school and you have a grade of X, then we'll consider that to be equivalent to the college class, with the same title, so that high school students who have taken, let's say, algebra 2 will not have to even take the placement test here and be assumed that they already understand everything that we teach at this
Some high
level
school
of
algebra is
algebra.
bad. Some high school algebra 2 teachers are bad, man. Like, you have to assess them to get to college because you get to another level. It's not high school anymore. You can't just just like, oh, we'll just turn in your homework, extra late. It's okay.
I mean, we can only ask for,
I mean, that's how people got by in high school. People get by in high school. Your teacher works. She's like, all right, well, coming at lunch, you can turn it in late, or come in lunch for the next week, and I'll make sure that you can get a better grade in your test. Like not necessarily saying guarantee a better grade in your test, but she'll help you improve. It's like there's all this extra work you can do in high school you can't do in college, and like to say that. Just by setting the university or the college level at such level without having that recognition is just to say that everyone all of a sudden at every high school is on equal ground when that's not true because different high schools have different economic
Yep.
status and different ability of access to information. Like some high schools are straight up having like tutors come to their houses as students because they're so wealthy. Other high schools, they're lucky if they get 5 minutes to study on their own when they get home.
And that's exactly why I think that high schools should be given funding based off the. It should be inverse. The lower the school test, the more funding they should get, not the other way around.
Well,
They should be.
The whole one bar to compare with how schools get funding by just performance is flawed to begin with.
Yeah.
You can't just use one measure to compare whether they're worthy of funding or whether they need it or not. It has to be a multi-dimensional measurement.
I think it's more complicated. I would have to do more
That's what's
research to have
complicated.
the
It's
actual.
multi-dimensional.
Well, yeah, of course I know, but I'm not sure that the actual funding system is one dimensional.
Yeah.
Because I have a.
We can watch it tick through.
Yep. Yep. It's getting back. It's getting back. Oh, it's done. It is done. All right.
E9.
Okay. So the question now is E9 the right answer? Okay. So let's figure this out. E is 14. So 14 times 16 is let's see. That's 84, right? 84. Yeah. So this is 224, and then plus what? A 9. That's 233. Yep, we got it. Is the stack pointer balanced? Okay, that's the next question. Okay, let's stop the clock. So we'll check the stack pointer. Stack pointer is balanced. So as far as I can tell, the program seems to run correctly. Isn't that fun?
What's C point to?
Huh?
What's C point? How deep in memory do we go? Because C never gets incremented. Never gets incremented past the parameter. So how far deep can you go in the memory?
Well, you can. Okay, there are two ways to figure that out.
Click on it, can't you? Click on the wire.
This one? EC?
The wire too? Yeah. Oh, yeah. I calculated it, I guess so.
Yeah, it's already calculated. We know that E9 is 233, so EC is plus 3. Yeah, plus 3, so that's 236. So 236, we have 256 bytes to begin with. Do the subtraction, we used up 20 bytes?
Wow.
That cannot be right. It's got to be using a little bit more than that. So C is
No,
not.
that's just the last parameter that was stored because it actually went down a little bit more.
Yeah.
Because we had to go to return it.
Yeah, it has to go down a little bit more. But you can also tell from the RAM content, how far it got. So it got all the way down here.
Which is EC.
Which is no, that's E4.
E4? Oh, E4.
Yeah, that's the E4. Yep. Yep, so we got plenty of space. Cool. All right, so are we good with this? All right. So with today's class, okay, so now we can move on to what I originally planned for today. And this is good too. I mean, just getting this solution out is good. So what I'm going to do today, or what I originally planned to do today, is to get into structures. We started to talk about structures in this class. In the previous class, on Monday, do you guys remember?
Right, because the structure has so many bits allocated to spaces.
So many bytes. Yep. Okay. So in class, during lecture, I was planning to show you an example of linked list. Okay, so I'm just going to download this. This is a zip file that has multiple files inside. So once you download the zip file, you just go to the folder, or in Windows you just click on it and then zip it. So it will give you 3 files. One is a compilable, syntactically correct and implementationally correct C file, so you can actually compile this, run it in GDB, and figure out exactly what it does. So I'm going to give you a brief description of what this is, and then we move on to the assembly code. Okay. So first of all, we have pound include std standard integer.h just to get uint underscore t, those things defined. And then we have a structure definition here. A structure definition is kind of the same as a class definition. The only difference is every member of a struct is public, and you cannot have methods inside a struct. Okay, so it has more restrictions. Doesn't really matter because all we need is to have 2 members. The first member is called v. That's the name of the member. Is an 8-bit integer. The second member is next. It is a pointer to a struct x. Okay. This is not recursion. This has nothing to do with recursion at all. Just because we are inside the definition of a struct x does not mean that we cannot use struct x pointer to define a particular member in that structure. Now, without the asterisk, that would be a big problem. Okay, that would totally be recursive. But with an asterisk, it is not recursive anymore. Why not? Because every pointer has the same size. It doesn't matter whether you're talking about a pointer to an integer, a pointer to a char, a pointer to a big, huge structure. A pointer with a 64-bit architecture is always 64-bit wide. A pointer in the TTP is always 8-bit wide. So it doesn't really matter what it's pointing to. The pointer itself has a fixed size. So that means, knowing that, I can now tell you how big a struct x is. It is the byte plus whatever a pointer is going to take up in terms of memory. Is that making any sense? Do you guys understand why it is quote unquote not a recursive concept in this case? Okay, all right. So knowing that it is not recursive, we can now define global variables. I usually do not like global variables, but in this case I use it because this is a very easy way to define a static linked list. So the first one, okay, I would recommend that you read it backwards. Read N1 first, okay? So the definition of N1 is the name of a global variable. It has a type of struct x, and it is initialized with the following things. Okay, so the first number, which is 16, goes to member v. The second thing, which is the address of N2, goes to next. Is that okay? So that's how I initialize the global variable called N1. N2 has a v or value of 5, and the next is the address of N3. N3 has a v value of 2, and it is not pointing anywhere. This is a null pointer, which is very typical that we use a null pointer to say, okay, I'm not pointing to any structure anymore. I'm the last one.
What's the difference between 0 and the actual null pointer?
There's no difference.
Okay.
I guess null may be defined as void pointer in parentheses and then a 0, but 0 is a special value. It does not need to be casted. 0 can be used as a Boolean, a pointer, integer, floating point number, and so on and so forth. So it has a very universal.
It's every type.
Yeah, the compiler can coerce it into basically all scalar types. So that's why I can just put a 0 here. Null makes it easier to read because you're not looking at a numerical value. And most people, they are trained, from science, computer science textbooks to recognize null as a special value. But in C and C++, 0 works just as well as null. Now that doesn't work in Java, doesn't work in many other programming languages where they have explicitly something called null to basically say, okay, this reference is no longer pointing to an actual thing. So. But in C and C++, it works out this way. Okay. Okay, so in main, this is what we do. PTR pointer is a pointer to a struct X. I have an array of 3 8-bit integers. I have an index called I, and here's a pointer. The pointer is initialized to the address of n1. So the idea is I want to track down all of these structures, go to the next one, track down that one, go to the next one until I hit the null pointer. Then I go like, okay, I'm done with this linked list. This concept is called a linked list because each structure or each struct X has a link to the next one, to the next one, and then the last one has a null pointer to basically say, I'm the last one, I don't have a next one anymore. Is that okay so far or not? The concept may be new because this is a data structure kind of concept, but the language constructs should not be new because these are all standard C concepts. Are we good so far? Okay. So this loop here is, so the initialization also includes I being initialized to 0. And the loop is saying as long as pointer is not null, in other words, as long as I have not traversed all the way to the end of the linked list, do the following. Array bracket I equals to the V member of whatever structure the PTR is pointing to. Are we really sure that PTR is pointing to something that is actually existing at this point? Yep, because PTR is not null. So we are assuming that, so that's a good assumption that PTR is in fact pointing to a structure, and we just need the V member of the structure, put it into array bracket I. Increment I so that we can store to the next location of the array, and then PTR gets PTR next. In other words, we take the next member of the structure pointed to by PTR, okay? That by itself is a pointer to a struct X. And then we put it back into the local variable PTR, and then it goes back and check, is that null? So it will keep traversing to the next item until PTR itself is 0. Then it knows I'm done, I have reached the end of this particular list. And then we just get out, we return. That's it. So with this C code, you can probably expect the values in the array when this is all done is going to be 16, 5, and 2. Because it's just following that order to put all of those values into the array. Is that okay? So now the question is, how is this done in assembly? Okay, so I can do a v split and then go to the other one and look at list.ttp-asm, which is the assembly version of all of this stuff. Okay, so the first thing first, okay, so when I'm basically following the same order as the C code, so the first thing is I need to create not local, these are global variables, they're statically defined. So I have to define n3, n2, and n1, and the way to do it in assembly is just like that. n3 is a label now, but under that label we have 2 bytes. The first byte is corresponding to the V member. The second byte is corresponding to the next member. Is that okay? We have n2, same deal. Okay, the V member has a value of 5. The next member has the address of n3. But in this case, because we're dealing with assembly, a label is already the symbolic name of a address. So there's no need to take the address of, because n3 itself is representing an address already. So there's a little bit of adjustment you have to kind of adjust in your head. And then n1 is kind of the same deal. Member V of n1 has a value of 16. Member next is the address of n2, which is the label n2 in this case. So are we still doing okay so far with the assembly code? How the structures are represented? Okay, all right. So now we move on to the main program. So in the main program, I basically draw a map of how the stack should be used. So in this case, because PTR is the first local variable, I'm going to assume that it has the lowest address. array 3, of AB integers is going to be the next 3 bytes, and then I is the last byte. So from the stack perspective, I have I, and then the 3 elements corresponding to the array, and then PTR on the stack. And then D obviously is going to point to PTR because that's the last thing that we push on the stack, or last thing that we reserve on the stack. Do we have any questions about that part?
So technically, main's not responsible for initializing stack pointer, right?
Main needs to adjust the stack pointer for all of the local variables to allocate space for all the local variables.
It's different from the lab. When we did the lab just now, you didn't do that in main.
I did.
No, it was done before main. So.
No, I did that. I did a single decrement D to allocate the one single local variable X
No, I'm saying
in main. Initialize?
In the lab earlier.
The initialization is not a part of main. That is outside of main.
Okay, that's what I was saying.
Okay, yeah. Sorry, I misunderstood your question. The initialization of the nodes or the struct X is actually outside of main. It is just statically initialized so that when you load the program, it is automatically there already. Okay? Yep. Lower. Because, in my notation, if it looks to be higher up, it is at a higher location, or the address is higher. Yeah, I encounter PTR first when we are parsing, but it is going to have a lowest address because that's how most people or most compilers would do it too. If you define local variables x, y, and z, regardless of the type, x is going to have an address that's lower than y, and y is going to have an address that's lower than z. That's a convention. I don't think it's a part of the C specification, but because that's what most compilers would do, I'm going to follow that convention. Is that okay?
So even though you encounter that statement first,
Mm-hmm.
struct X BTR, you'll skip that and skip the next.
Correct. Now, you might think that from the perspective of a compiler, this is taking extra work, right? But from the compiler's perspective, when it compiles the program, most compilers have not compilers, but most architectures have what we call a frame pointer. So the frame pointer is at a fixed point. Okay, it's just pointing at a fixed place. So when you declare more local variables, it doesn't really change a whole lot. So the compiler doesn't really have to do a whole lot more in order to cater for the definition of local variables. Yep. Question?
Yeah, I mean, so when the compiler reads the code, I guess it all comes in. So it's a no. I mean, I don't know when the program runs, it knows just to go straight to main to start. But even though we initialize, I don't know, because that sub D register means that we reset the stack pointer right there. So how do we have anything on the stack anymore?
How do we?
Because you have I array, and the array things, and then right above it though, you just set the stack back to 0. So
No, but this is allocating for that space. So sub DD really should be outside of main.
that's all I'm saying.
Yeah. So this line really should be from the perspective of where it really should be. Oops. This really should be there. It really should be there because it is not the subroutine that is initializing the stack pointer.
No.
Okay, we're good. Okay. So we are. So these two instructions are here to initialize, so that we have the space allocated for all the local variables because I need 5 bytes for the local variables. So I'm decreasing the stack pointer by 5 to allocate for the local variables. Is that okay? Any questions about that part? No? It's all good? Okay. So with this done, the first thing that actually needs to do here is I need to initialize pointer PTR, which is a local variable, with the address of N1. That's what the C code is doing. In the assembly code, it is a lot easier because D as a stack pointer is now pointing to PTR already because PTR is at the lowest portion of the stack. So the stack pointer is pointing to PTR already. N1, as a label, is the actual address corresponding to what we know as variable n1 in the C code. So by doing an LDIA n1 and then storing a to whatever d points to, that accomplishes PTR equals to the address of n1 in the C code. Is that part okay? So we are done initializing the pointer so that it points to the first thing of the linked list. Is that okay? No questions? Okay. Moving on to the next instruction, we have to initialize I to 0. So we have to figure out where's I on the stack. Okay. Well, I is 4 bytes, on top of what D points to. I cannot change D, so I'm going to copy. So I load 4 into A, and then I add A to C, after copying C. So somebody commented in the other class and said, oh, this can be done with fewer instructions, and I agree. Can you guys see how this can be done with fewer instructions? Okay, so I'm going to show you how to do it with fewer instructions.
Take out the copy register and the
Yep.
dereference.
So you just do, okay. I'm trying to preserve the rest of this code, so I still want C to end up with that address. So we basically do it like this, do it like that, get rid of that. Okay, let's check it. Okay, does it make sense? I load a 4 into C, register C. C has a value of 4. Then I add whatever D the stack pointer has to register C, which already has a value of 4. Hey, that's D plus 4, right? And I store that D plus 4 into register C. I can get rid of the next instruction will complete the operation. So after these two instructions, C will become the address of local variable I. Is that okay? So instead of using the CPR and then LDIA with something and then adding that to register C, it's just a little bit more streamlined. Instead of 3 instructions, it's 2.
Instead of incrementing 4 times.
Hmm?
Instead of incrementing 4 times.
Or incrementing 4 times, yeah, that would be the kind of obvious way, but also not very optimized way. Yep. Okay, cool. So then the next one is getting A to become 0. Okay, I can use a LDIA 0 to do it, but I can also subtract A from A. Then A is also guaranteed to be 0. And then we just store A to whatever C points to, but C has the address of I. So when I store A which has 0 to whatever C is pointing to, I'm initializing I to 0. Is that okay? Okay. Then we have a loop. Okay, so the loop is checking whether PTR is 0 or not. As long as PTR is non-zero, we stay in the loop. As soon as PTR becomes 0, we get out of the loop. So how do we do that? Well, fortunately, the stack pointer is still pointing to PTR. So we dereference the stack pointer into register A. So register A is now actually PTR. This is the usual trick that I did, in this class many times, using AND AA to check whether it is 0 or not. Now, it cannot replace a general comparison. But if you just want to compare to 0 and see whether something is 0 or not, AND AA can get a job done, and it can save you, like at least 1 instruction to do it. And then we have JCI to while end. It means if PTR is 0, then we go to while end, which is a label that exits the loop. Is that okay? So that's the control structure, okay, of while PTR. All right, so let's page down here. What is inside the loop is actually the difficult part of this program. Because the first line inside the loop is to say, figure out the the value of member V of the structure pointed to by PTR. How do we do that? Well, we cannot do it unless we know what PTR is. So the first thing we do inside the loop is, oh, it's very handy because A already has the value of PTR. because of the way we set up the comparison, the condition of the loop. So register A already is PTR when we get to the body of the loop. So we just go like, oh, we just dereference it once, and now we have whatever PTR points to. Well, PTR doesn't point to a particular thing. It points to a structure, right? But the first member of a structure has the same address as the structure itself. Is that okay? You guys want me to say that one more time? No? Okay. The address of the first member of a structure has the same address as the structure itself. Okay. So that means in this line here, LDAA is going to retrieve the first byte of the entire structure, which turns out to be member V, because member V is the first member of the entire structure. So now we have A. Okay, let me go back here. So now we have register A being whatever the member V of whatever PTR points to, and then we push it on the stack because it's useful, but I erroneously assumed that I would need more registers, so I push it on the stack so that I can use register A after this. As it turns out, we actually have enough registers without pushing it on the stack. But it's okay, it's just going to waste more processing cycles, but it's not wrong. It is just a little bit too prudent. Okay, so this part is pushing, member V of whatever structure is pointed to by PTR on the stack. Then we need to figure out where is element I of this array. Now that is something that we haven't seen before, which is it is array indexing. Okay, well I suppose you can at least you have to figure out what I is first, right? Can we agree on that? Okay, so we figure out what I is. To figure out what I is, I'm using that trick again because I is now 5 bytes away from where the stack pointer points to. But it was 4 bytes away. How come it's 5 bytes now? Yep, we just put some temporary values on the stack that adjust. So now you have to remember and say that, oh, we got one more thing on the stack, so I have to add 5 to the stack pointer to get to local variable I. Okay, so that's what this is doing. So by the when I'm done with add AD, A becomes the address of I. Do one dereference, A becomes I. Okay, so cool. I have local variable I in register A at this point. That's my index. What are you going to do with the index to find out where is the address of member I of this particular array? We already know that all members or all elements of this array is only 1 byte wide. So how do we find the address of element I of this array? What piece of information is missing? The address of the entire array. Where does it start, right? Where does this array start? Okay, so we need to figure that out.
It's one value less than I.
It is not. The beginning of the array is not 1 byte below the address of I. It is actually 3 bytes below the address of I.
Backwards.
Yep, because we do things in a slightly backward way. But that's okay. We can just recompute the whole thing. So we need to find out what the address is for array. So we just put a 2 into B and then add D to B. So it's basically D plus 2, which makes sense because when you look at the earlier picture, it should be D plus 1. But since we just pushed one thing on the stack, it is now D plus 2. So D plus 2 is the address of the entire array. So when you add I, which is in register A, to the address of the entire array, that sum is now the address of element I of this array. Is that making any sense? Now, when I just talk about it, it may not make a whole lot of sense, but when you draw a picture, it's easy to understand. There is a picture that I have in here. this is also the beginning of the entire array. Okay, so when I is 1, for instance, where is array bracket 1? Array bracket I. It's just 1 byte on top of the beginning of the entire array. This, by the way, is the reason why we have zero-oriented indexing. Okay, zero oriented indexing means the first element of an array has an index of 0. Now, I'm almost 100% certain that to most people it is counterintuitive. How come the first element is not index 1? How come it's index 0? This is why. Because the first element is at the very beginning of the entire array. So that's why it is called element 0. Because it is at the very beginning, there is 0 element between that and the beginning of the array. That is why it's called element 0. And it makes it easier to compute the address, because otherwise you have to subtract 1 first. Doing it this way, you don't have to subtract 1 first. Is that okay? All right. So, are we doing okay so far with this code here? Okay. So now that we have the address of array bracket I stored in register A and the value of member V of whatever PTR points to is on the stack. So the first thing we do is we retrieve that from the stack using these 2 lines, and then we just store that to whatever A points to, because register A is now pointing to array bracket I. So by storing, it is automatically doing a dereference, and then B has the value of member V of the structure pointed to by PTR. So that accomplishes the first line of code in the body of while. So are you guys starting to appreciate, the C compiler? One line of code, and it's not even very convoluted, in C translates to from here to here. So we are talking about 10 lines of code in assembly. Someone may be able to optimize this a little bit and save 1 or 2 lines, but probably not more than that. All right, so next line is incrementing I. I think that's relatively easy. We first compute the address of I, retrieve I itself, increment, and then store it back to where I is, and we're done with the increment. Is that okay? All right. Any questions?
Since we know how wide or how many elements there are we gonna like just code out as if every element went through the loop, or is it we gonna set up a structure so it run through like if we changed how many elements were in it, it would just become the same code?
You mean with this 3 here?
Like we changed it to 4. Are we gonna when we're done with the machine code? If we changed it to 4.
Change what to 4?
The array size.
Uh-huh.
Still like run like normal.
Yeah. Yeah, if you change the size of the array to 4, that means you're just wasting 1 byte. It is not going to be initialized at all by this code, but it will still run. Yep. Okay. And then the last line of code inside the loop is this one. We have to first retrieve member X next of the structure pointed to by PTR, and that's done by the first 3 lines. And then we have to figure out where PTR is. But PTR is already pointed to by the stack pointer, so that makes it very easy. So that's why these 4 lines is implementing this line of code in C. So are we good so far with this? Yes? All right. Okay, so I might as well talk about your homework assignment a little bit here, because otherwise I would just be setting up everything like this over at the lab, because you need a little bit more information to get started with your homework assignment. Okay, so I'm gonna get rid of this. This code, by the way, is already on the server, in Canvas. It's called list for linked list.zip. So you can download it, just play with it, if you want to, track it down. And it's fully debugged already. I ran this code already, and it was working 100%. So the next thing you need to do is an actual homework assignment. So if this is a demonstration, the next question is, what is your homework assignment, right? Your lab involves the usual things. It has a few questions, that you can answer in almost no time in this case. But the last question is the implementation of a binary search tree traversal. Okay, so people think like, but I haven't even taken data structure yet, so what am I going to do about this? This is not fair. Well, I'll tell you, it is 100% fair. Because one, I'm not asking you to write the code itself in C. The C code is already done. Okay, in a data structure class, you are the one who's going to write the code in C. This is already given to you. Okay. Second thing is I'm giving you everything that you need to start with. Okay, so let me go back and show you what you can start with. It's called struct.zip. Okay, so download that file, unzip it, and then look at the content. So I'm gonna do it here because I want to show you what is in it. So unzip struct.zip. So it's got two files. One is a C file, the other one is a TTP-ASM file, which you can use as a starting point. Okay, so we'll take a look at the C code first. Okay, so we'll do the same thing. Okay, struct.c. Okay, -o dash. It is contagious, isn't it? Now I'm gonna bring a metronome next time because I think your beat is off a little bit. Tick tock, tick tock. And we'll make it a 2-beat thing. My metronome, some of the metronomes can go like tick, ding, tock, ding, tock, ding. Because if you have a 3-4 time signature, it will do a tock, tock, ding, tock, tock, ding. Exactly. And then we add percussion and all that. All right, so I already did some work for you. I simplified traverse so that some of the kind of really difficult part or confusing part is gone. The auto increment of array inside this statement is gone. So this one has no auto increment whatsoever. Okay, makes it easier. So you look at this code and go like, all right, can we do this? Do we know how to do it? In the code that I showed you a little bit earlier, it has a while loop. As long as the pointer PTR is not null, we're going to keep ourselves in the loop, right? This one has a conditional statement. Same concept. If PTR is not null, do this, but only once. In a way, it is easier than the sample code that I showed you a little bit earlier. It has got recursion because if PTR is not null, I am going to call traverse with member L first, and then we'll call it one more time with member R. Is that difficult? Did the code earlier show you how to access a member of a structure pointed to by pointer? Yes. But somebody's going to say, but in that code, PTR is a local variable. This PTR is a parameter. What is the difference? Exactly. The offset from the stack pointer to PTR is different this time, okay? But it is still on the stack. It is still relative. It's still at a fixed offset from where D points to. So you're going to use the same mechanism to access it. It's just that the offset is slightly different, okay? In terms of the second parameter, super easy. Whatever you get is what you pass recursively. How much easier can it get? Whatever you have, you just pass it along. There's no increment, no decrement, no nothing, okay? You just pass along whatever you get, okay? And I can see people frowning already at the double asterisk. Because this part is not a problem, right? PTR points to value, which is member V, of the other code. Easy peasy, because value is the first member of the structure pointed to by PTR. We saw how to do that already. That part is easy peasy. This part is like, holy smokes, how do we do that? It's much easier than array indexing. There's no I, there's no adding. Okay, how do we get to array? What is array? Array is a parameter, right? So how do we get to array? Well, worst case scenario, you start with register D, the stack pointer. You calculate how many bytes it is off from that, right? You calculate the address, you stash it into a register. Then you get the address of array. Once you get to the address of array, how do you get to array? Dereference. Once you get to array, how do you get to what array points to? Dereference. Once you get to what array points to, how do you get to what is pointed to by what is pointed to by array? One more dereference. Yep, so you just have to count, okay? And trust me, I think last time I checked, everyone in this class has enough finger on one hand to count the number of the references necessary in this code. Okay? Now, if you went with somebody to cut down some walnut trees over the weekend and did not know of any accidents, you may not have enough fingers, but last time I checked, everybody has enough fingers. On one hand, I'm not talking about two hands, one hand. Okay? So this line of code is actually not that difficult. Okay? It is a test of concept, whether you understand what dereferencing is really doing, and also counting how many times you have to dereference before you say, okay, that's what I need. Okay, this is what I need to do a ST instead of LD to do the dereferencing. Okay? Next line. We're adding one to not array, but what array points to. Same idea. First thing, get to the address of array. Second thing, get to array. Third thing, get to what array points to. Add one to that thing. Done. Okay? I would say in some way this program is actually easier than Fibonacci, because there's no need to save the return value of an earlier invocation on the stack. Like Fibonacci. Huh?
That was easy.
This one is actually not that hard. I mean, it really is. It's harder to debug. Okay, so this is what I need to really get to, is how do you debug this program? How do you write this program, and how do you debug this program? I'm going to write this entire program, and then we'll run it in the simulator and see if it works. Have all the fingers crossed. Right?
No.
That is not going to work well. Okay, that's not going to end well. Okay, so what you need to do is to say, okay, let's forget about the recursion part. Okay, in other words, now remember this code actually compiles. In other words, if you simplify the program,
Where's main?
main is already done.
What is it?
Main's right here.
Just traverse? Okay.
Yeah, main just calls traverse once. And it is already implemented on the other side. So this main is already done.
Okay.
Yeah, so you're only implementing traverse, which I think that makes it easier than Fibonacci, because in Fibonacci, you have to deal with main too. This main is already done, and that main is equivalent to the C code as well. So the first thing you want to do is to say, I'm not going to deal with recursion now. Okay, I'm just going to do it once and see what it does. And what it's going to do is it's going to take the value of the first thing, which is 5 here. It's going to store 5 into the local variable array in main. That's it. That's all it's going to do. And it will also increment. A pointer in main, which is p sorted. So p sorted is going to be incremented, so it points to the next element. And that's the side effect. But remember, you can actually run the C code. Even if you modify the C code, you can just run it. So this is what I would recommend, is to run it with the recursion commented out, or do not implement the recursion part, do it in C first, and then check out what this C code is going to do by single stepping into it and say, oh, I can see it is accessing that array from main. It is now incrementing that pointer from main, and that's all it's doing. Okay. Once you understand what this code is going to do, implement traverse without recursion and do it like this first. Because if you cannot get this part done, then recursion is not going to work at all. So you got to have this part done first. Is that okay? Second thing you can test is, instead of actually passing the address of a structure to traverse, pass a null pointer to traverse. Make sure that traverse skips everything and doesn't do a single thing. It's easy to check, easy to do, but it is important that you check that first, because if the check for pointer being 0 is not done correctly, your recursion is not going to end. And if your recursion is not ending, it's going to clobber the code space, the actual opcode, and then your program is going to go crazy after that. So it's important to make sure that when PTR is 0, it stops. It doesn't do a single thing, it just returns. Is that okay? So don't be ambitious or over ambitious and try to implement the entire subroutine and then use the entire structure like this. The other thing, if you really want to test the entire thing, including the recursive part, okay, so let me remove the comment of traverse, or the recursive part of traverse. Okay, so let's say you finish the entire code. Okay, my suggestion is, don't start with N1. Start with N5 or N4. The reason why you want to start with N5 or N4 is because N4 and N5, even though they will do the recursion is not going to do a single thing, because they don't have any left or right child. So I would kind of do it that way. Just one more thing, if you want to look at a graphical representation of these nodes, so to speak, the node that has a value of 5 is what we call the root of a binary search tree. And then this is the L, this is the R, the left and the right hand side. And in this case, this is N2, and N2 has a value of 3. And then N2 has no left child, but has a right child of N4. This is 4. And on the right hand side, we have 10 and 9. So this is kind of the graphical representation of the binary search tree. What the code in C is going to do, you can track it down in GDB. So basically what it does is, it will first traverse the left-hand side, then it will record its own value into the array, and it will traverse the right-hand side.
So this binary tree is not sorted, right?
It is a binary search tree, and the idea is the traversal will return sorted values. Because what happens, okay, so if you want to look at actually what happens, well, I don't have any different colors. I got, yeah, boring. Okay, so what it's going to do is, it will first get here first, right? So it will get here first, and then it will traverse into here, and then it will recognize there's nothing here. It will go back to here, and this is when it will write the value of 3 into the array and increment the pointer. Then it will traverse the right hand side, and then from here it will attempt to traverse the left hand side of 4. There's nothing, so it will go back to here. So when it gets back to here, it will write 4 into the array. Then it will attempt to traverse the right hand side. There's no right hand side, it doesn't do a single thing. It gets back here, but there's nothing to do when it gets back here, because that will be after the second recursion. Then it will go back to here after the second recursion, and there's nothing to do. Then we'll get back here. So at this point, it is going to write the value of 5 to the array. Then it will traverse the right-hand side of that tree. The right-hand side of this tree is over here, but it's not going to record the 10 because it wants to traverse the left-hand side first. So it will go here. So this is step 6. This is going to be step 7. And it will try to traverse the left-hand side of the 9. There's none. It will go back to 9. And that is when it will write the value of 9 to the array. Then it will attempt to traverse the right-hand side of this 9. There's none. It will go back to here. And then it will go back to here.
Select step 8.
And then it will write the 10 to the array. Then it will attempt to traverse the right-hand side of the 10. There's nothing there. Goes back to the 10, but then we're concluding there's nothing to do at this point. Go back to here, there's nothing to do, and that concludes the whole thing. So the order of writing the values into the array is going to be 3, 4, 5, 9, 10. So those are the values you should expect in the array when everything is done. The sequencing of how everything is done here can be demonstrated by GDB. In other words, you compile the C code here, you single step, that will show you how everything is done. Is that okay? So the only part that is really tricky about this is how do you debug it. Okay, the code itself is not a big problem. It is how you debug it that can be a little bit tricky. All right. Okay, so I'm gonna stop the recorder, and then we'll move on to the lab for those of you who want to give it a shot